Hi everyone, it's my pleasure to introduce Mickael Binois today. You have met him, he was a student of mine early days. Then this is PhD at Mines Saint-Etienne and Renault, did a few postdocs in Louisiana Tech, Chicago, and now he's a researcher at Sophia Antipolis in area, southeast of France. So Mickael has worked a lot on measure optimization and active learning, and lots of GPs applying it to different things. So really keen to hear about what you're going to talk about today.
Thank you, Victor. And thank you very much for the invitation. So today I plan on speaking to you about replication in active learning tasks. So I have a few variations on this topic. I will go up probably back and forth between different ideas that are more or less going in the same direction. So as it's is a remote seminar, I do not really, I may go too fast or things, so please interrupt me if it's not clear or to explain more some topics. It's let's make it not too formal, so yeah, feel free to interrupt me. So I will start by a motivating example that I did during COVID. So I had collaborators in New Chicago from my postdoc years at Argonne. So they had this great model of the population of Chicago, and it's an agent-based model, and it has up to like 2.7 million agents that are like living their lives in Chicago. So with interactions, they can go to school, to bars, like it's really a synthetic population that is supposed to be as representative as possible of what people are doing in Chicago, and it's based on the real features of the city. So then there was the COVID, and they actually repurposed this simulator to be used to monitor and to help decision makers during the COVID period. So that for this, they kind of had to work on proposing scenarios and working with the public health department there to have to get some like almost real-time feedback on what was going on and what were the ideas, and should you be more strict or more relaxed on what you do and like the measures. So with this, in fact, what they were doing under the hood was calibrating this city COVID simulator that had like 9 real like parameters to calibrate that were corresponding to things that are difficult to measure or to get just from the data, which, for instance, that would be out of household activity level, transmission reduction from person to person. So these types of parameters that were not well known. So they used the data that they were provided by the officials, and they were running their simulator and trying to get the good values for this. So their method of choice for this is some Bayesian method to get posterior distributions on these posteriors. But they also wanted to get like scalar good parameters for like selecting just a few scenarios to get to try some like policy on them. So that's where I arrived kind of, and the idea was how to actually find good sets of parameters, not helping also the estimation of the posterior calibration, but mostly also getting good values. So then that's when it become a multi-objective optimization problem. So they are mostly interested in 2 outputs, which were the death count and also the hospitalization rate. So the red dots are actually what was observed. So it evolved over time. And the black lines are just outputs of the simulators. So as you can see, it's actually a pretty noisy runs that you get. And that's the main difficulty of this problem, is that if you run the same set of parameters, but you initialize a bit differently the agents, then you may get a very different outcome. And so to make it work, we had to like go from time series data to actually scalar data. So we aggregated the error with some weights depending on the time. So it was putting more weight on the most recent data. And if we look at like two designs and two different for many different trajectories, you can see that the distribution of the error is actually quite it's not Gaussian at all, and it's there is a shift. Then you have also a large spread that you can observe. So that was a difficult problem, and yeah, just doing one simulation do not provide you with much information. So these all the challenges that were there at first are those. So the signal to noise ratio is quite low, and so that you need to have a larger evaluation budget so that you get you can actually predict and be useful in this case. As we have seen, the noise is heteroscedastic and clearly non-Gaussian, even after the scalarization of the outputs. It was also in a context where they had access to a cluster, and since it was a high priority, the idea was to run hundreds of such a simulator. So they were able to like clearly fill a huge cluster they have at Argonne. So you can run hundreds of runs, and these they take approximately 10 minutes. It was even worse than this from the BO point of view, is that if you take too much time to give the sets of runs that you want to conduct in parallel, then the cluster usage is actually looking bad. So you need to be to provide quickly what you want to evaluate next, so that you spend most time actually running the simulator and not selecting the best points to run. So that's the point on the cluster usage. And it was in this context, it was very important to have back to this motivating problem later. But first, I will motivate and contextualize a bit more the problem. So in this talk, I will discuss expensive to evaluate black box simulator, but maybe contrarily to what is usually considered as expensive, here, since it will be noisy simulators, expensive would just mean that I don't want to waste evaluations, but I also don't want to spend 1 hour to select the next point. So there is this timing trade-off that's ways to see this. So it can be either you can go very fast to provide new points, or you can spend more time. And that's really an application dependent problem. I won't really focus on high dimension. That's another topic. But yeah, we take the usual moderate number of variables. And considering possibly a few outputs, even though I will mostly illustrate with one output because it's easier to make. And the key feature is that also like I will take noisy simulators, even though sometimes I can illustrate on deterministic problems just to show what's going on. All right, so for the background, I will go super quickly on the GPs and the BO IDs because you know this very well. So not to bore you. So I'm using a regular GP, zero mean. I'm not using anything too fancy there except just to define a notation. Mu n will be the predictive mean, and sigma squared n will be the predictive variance. So then, yeah, here's the typical Gaussian process cartoon. As you know, you can get draws from the posteriors, which are the colored lines, but here we won't make really use of it. So as you also know, when you have noise in your observations, it's quite easy actually to handle. You just add a constant noise term to the diagonal of the covariance matrix, and then you stop interpolating, but you can filter the noise. So that's usually sufficient. But when you have a very low signal to noise ratio and that the variance is changing over the space, then maybe it's important to also model this. So that will be the main GP workhorse in this presentation. that would be a heteroscedastic Gaussian process. So the main change with respect to the previous slides is that for the diagonal covariance matrix, for the covariance matrix, we have the diagonal term that depends on the variance at the given the location where we are looking at. So it's only this diagonal matrix. So it means that we are not just interested in the probability of like the posterior distribution on f of x given the data. We are also interested in predicting the noise variance at a given location. And of course, in practice, you never have access to the variance process, so you need to do something about it. So the main advantage of having this model is that you have better variance prediction. Because if you really look at some examples, if we take like a simple data set that's known as the motorcycle accidents data, these are the black points. There are actually some replicates in it, but I will insist on this later. If you look at the predictive mean using a constant noise, then you won't see much difference between the left and the right panel. It's because the GP is good at filtering noise anyway, even if the noise model is incorrect. But when you also consider that the noise variance can change over its time, then the predictive intervals are actually much better. And you can look at either the predictive intervals on the mean that are represented in red, or you can look at the predictive intervals for a new observation that are given by the green line. And here in this case, it's quite clear that if you're able to change the noise variance over the time, then you're able to make a much better job. So that's the motivation to go heteroscedastic. It's that you have better prediction intervals and you can predict the variance at a new location. How to do it? There are several ways. So one very important option is to use replicates. So for notations, I will introduce a few more. So that you assume that you have been repeating observations at a given unique location. So the unique location would be the X bar. And then you will usually assume that they are much less than the total number of observations. Then you have access to every individual observation for these replicates. But from them, you can compute what's the average value at a given point where you have been doing AI replicates. From this, you can compute the empirical covariance, the empirical variance of the noise. And as you can see, it depends on the squared of the noise variance divided by the number of replicates. So if you look at the standard deviation, it decreases actually in the square root of the number of replicates. So it's something I will go back also again. So that's an idea that has been used in the so-called stochastic rigging model. And in fact, if you use these average quantities, so the sigma at n, which is the matrix of the noise variance divided by the number of replicates and the average observations, then you get a predictor that is unbiased, and it has the same properties as the original GP model. And you can also show that the predictive values are exactly the same as the one that you get if you do not consider that you have replicates. So that's a very important property. And so in practice, what do you do is that you don't just compute the empirical moments, you also put a second GP on these noise variance estimates, and then you use this to predict the variance for a new location. One main advantage out of this is that the original equations that were using the capital N quantities, they reduce to a small n cube complexity, and that's the limiting factor. So going from capital N cube to small n cube can be a huge if you have many replicates and you do not have many unique inputs. So the issue with this specific model is that you need some amount of replication to have accurate estimates of these sigma at values. And also, unless you actually put a second GP, you do not have access to the posterior variance at a new location, the posterior noise variance. So what you can do is actually to use some latent Gaussian process on the log variance. And by doing this, you have like two GPs that you need to make work together. And you assume that this noise variance will be a smooth function of the input space. So now the one issue with this is that you cannot get a closed form expression for this posterior. So there are many works that have been proposed to solve the problem with some approximations. So you go from full MCMC to some expectation maximization approximation. You also have variational versions. On the one I've been using, but that's not, it's just one possible example, is an approach just based on the maximum likelihood. So the advantage when you have this representation with two GPs is that you do not have to have replicates. So you can have replicates in some locations only. But if you have them, then you can exploit them for speed and also accuracy. So now I will motivate on some examples why actually having replicates is a good thing, not only for the computational complexity. So first, just for the training, so I did not speak too much about this, but there are hyperparameters that you need to fit. Usually go for the maximum likelihood, but that's just one option. And if you represent it on this data, and you have two hyperparameters, one is for the noise value, the other one is for the length scale. In fact, on this data set, you can have two scenarios. One is a deterministic fit with some very wiggly function, and the other one is a smoother function, but with noise. And here are the actual values. So as you can see, the likelihood is actually quite flat in between these two scenarios. So now one trick, in fact, to decide in between these two is just to replicate one point. And if you do this, here I just replicated one point, and it clearly gives that in this case, since these 2 points are different, then it's the noisy fit that is the good answer. So that's one thing that can help is that if you have replicates, then it will be easier to estimate the noise.
Hey, can I ask you a question just quickly?
Yeah.
So by replicating, what do you mean replicating? Like you adding like another point at the same place?
Yeah. Yeah.
But why your target basically is noisy or what?
So I'm assuming noisy observations, yeah. But if you don't know, it's always a good thing. Like you have a new black box problem that is provided to you by an engineer, I don't know. And it's not a bad idea to run it twice and see if you get the same results. Like I've seen cases where people were thinking, oh, it's a deterministic thing. And in fact, it's not. Or it was just that there is this seed parameter that was hidden. And once you remove it, then you get a noisy simulator.
Okay.
But
I would think that if you add like the same place, and I imagine that you're adding this point to your data set or something, then your K matrix is going to be like singular in that case. Or
if you do not have the diagonal matrix.
I see. Okay. Okay,
yeah.
Makes sense.
So yeah, once you add the diagonal, even with a
makes sense.
large one, then it's okay. And that's really what's going on in between going from these like sigma at or like averaged over estimates of the predictive variance and the original one that was just a large diagonal matrix with perhaps a constant term. Okay, so another illustration of why this may be useful. Say you have two different ways of handling like a Gaussian process regression problem. Either you can do 10 unique designs with 10 replicates, or you do just 100 unique designs without any replication. So in this case, if you compare the root mean squared error, you do actually slightly better when you replicate. The score here is something you need to maximize. It's the inverse of the NLPD that is sometimes used to estimate the likelihood of the data. So higher is better. And in this case, you actually are better also when you do replication. And an even perhaps more important thing is that if you look at time, it's like to get a factor of 10 reduction by just using the replication. So yeah, all of these are combined and they make a case for replication.
I didn't really understand this bit of time, what exactly you meant by this. Why is
So-
it faster with the replications?
So if you do a GP with 100 unique designs,
Yes.
it will scale with capital N equal 100.
Yes, I see what you mean from the previous slide. Okay.
But then if you have just 10 unique designs, it will depend on 10.
I see. Okay. That makes
There
sense.
is a capital N squared that is hidden somewhere, or even N linear R N. So it's really not something you will see in practice.
Yeah, that makes sense. Thank you.
Do you have a comparison to like, do you get most of the, do you need 10 replicas? You were saying before that like even 2 replicas helps with the kernel hyperparameters. If you did 2 replicas, would it be somewhere in between these or?
Some amount is fine. Like here, in fact, the black dots, they correspond to the averages, and the just the small circles, they are the data. So there are a few replicates. I think it's 122 points, but 90 unique designs. So as you can see, there are locations where there are no replicates, and some where you have just like 2, and sometimes you have more. So if you are using a second GP on the noise variance, then you can handle this case. If you are using the empirical estimate, like here, then you cannot compute the empirical variance when you have only one observation. So I guess my point is that if you make the same amount of replication everywhere, that's something that's easy to do. You compute the empirical variance and then you use it, and you fit a second GP on this. If you want to have some like varying replication, then you really need to get for a joint latent GP that is working for the variance, for the noise variance. Yeah. Cool. Any other question?
How do you pick the points where you want replicas? Do you have a principled way?
That's exactly the point of the reminder of the code. And it also joins the questions. Yeah. How many replicates do you want at every location?
Yeah.
What's the amount of effort you should put? Given that since the reduction of variance from a new replicate goes from it's a square root factor. So if you replicate too much, then you don't gain that much. So it's clearly a trade-off, yeah. And there are I will present some ways to handle this. So for this, I will go in a sequential design framework. So where we start from a given data set where you can do your favorite space filling initial design, typically some Latin hypercube. And then the way to go would be to update the Gaussian process model with new data and select where to put observations. And the question will not be only exploration or exploitation, it will also be replication. And the difference between exploitation and replication is really, if I exploit, do I get a new point, or actually I reuse an existing one, but I replicate it some more. So for this first part, I will use the IMSP criterion, which is the integrated mean squared prediction error. So that's the integral of the predictive variance on the mean over the domain. So that's this criterion is targeting global accuracy. So you want a GP that is accurate everywhere. Next, I will be using also the expected improvement but that would be in another part. So for all these works, what will be important is that for GP, once you have the GP posterior at with a given amount of data, you can actually get an idea of what will happen in the future. So if, say, I want to add one additional point, xn plus 1, and the observation will be yn plus 1, that is currently unknown, then I can express my predictive quantities depending on this new point and possibly new observation. The main point is that, as you can see here in this term in the middle, it does depend on the noise variance at the point where we'll add a new point. So we can get what will be the predictive mean after adding a new point, but this depends on yn plus 1. But what is cooler in a sense, and that's a GP feature, is that the predictive variance will not depend on this new observation. So you can go and get an idea of what will be the predictive variance after adding 10 new points or 100, and you have no need to evaluate to get this. And that's also true for the predictive covariance. So these expressions, they are only n squared instead of n cubed, if you are going for the naive update. And since they are analytical, you can use them for having closed form acquisition function. So from this, if we look at this integrated mean square prediction criterion, you can actually express it for when you add a new criterion. And this integral has a closed form for the typical separable kernels. It's because you can compute this integral of k times k over the domain in closed form for some of these typical kernels. So the good point with this is that you have an analytical expression for the integrated mean square prediction error, and you can actually simplify this the computation if you consider that you add a new point, if you consider that you replicate, because it's actually boils down to making a rank 1 update of a matrix that is multiplied by these W matrices that are the integrals of the kernel. So what is it useful for? So in fact, we used it to get a condition on when replication is actually the optimal thing to do. So it's a bit of a synthetic example in the sense that if you assume that you have 5 observations and that you know the noise variance, so that these were represented by the different line types and colors. So you have the blue one, that's one scenario for the noise variance, and you have the green one, that's another scenario. Then if you use this condition, that will give you this gray dotted line that is here. And in fact, if you use this condition, meaning that your noise variance is always above this gray line, then the optimal decision will be to replicate. And that's what you observe if you optimize this criterion, the EMSPE, under the scenario that the noise variance is the blue one, then you replicate. So it means that even theoretically, replicating can be the optimal thing to do rather than adding a new point. But if you do not satisfy this condition, that's the green scenario, then you add a new point instead of replicating. So that's one motivation, theoretical motivation to go replicating. In practice, how would you replicate? So there are many ways to go for it, but I will explain a few. So first, there is the numerical aspect out of it, is that if you optimize your acquisition function numerically, then replication may occur in these cases. One typical case is that if you have a compact domain, so like the typical hypercube, sometimes you will replicate on the corners just because that's the way it will do like true replicates on the corners. Otherwise, if you like get some, if you look at the values of, say I want to add a new point that is very close to an existing one, perhaps that should replicate and you enforce some threshold. Say if you are 10 minus 3 to a distance of 10 minus 3 to an existing point, then you just replicate. You can also look at the values of the acquisition function. If it's like a 1% change in between a new point and a replicate, maybe you can say that you replicate. There is also the very naive way of saying, okay, on my problem, I will do 10 replicates every time, but that's usually not the best way to go. Then I will go for, I will detail the looking ahead idea that is actually more interesting. So far, are there any other questions?
Maybe one quick precision on the criterion. You say it's analytical, but you still have an integral over the d dimensions, or can you split this into one integrals?
For the IMSP, if you have a separable kernel, then you do it. You can separate your integral. Yeah, it's like here you have sigma squared of n depend. It's actually just integrated the predictive vector, the covariance vector, and the covariance vector is separable. So you have a closed form expression. Where was it? Here. There's W matrix. It's actually the product of over the dimensions.
Okay, which is not exactly analytical, but it's one dimensional. So very accurate.
For maternities, for Gaussian, it depends if you consider that the error function is analytical or not. That's
okay. I see.
no. But otherwise, yeah, for matern, you get just polynomials and exponentials. Okay, so the following, I will give you 3 recipes to get replicates. So the main idea is that we want to keep a small number of unique designs and to have as much replicates as possible. So the one point for this is that once you add a new point, you will have to keep it until the end. So if you try many new designs at first, then the computational complexity will be large for the remaining of the task. Also, if you want to, one critical aspect is that when you look for a new design, it's like a continuous optimization most of the time, which is more expensive than just looking at the endpoints that you already have and say, oh, I want to replicate on the 6th one I visited during my search. So there is ideally, we would like for the best sequence of new designs and replicated ones, but this goes to the like a dynamical programming problem when you need to select what will go into in the future. And of course, that's too difficult. That's sometimes called the non-myopic strategies, but the optimization problem is too complex. So in this context, we propose to simplify the problem with this decision at each step. So either you add a new design now and you will replicate later for a few iterations, or you replicate now and then you will add a new design. So that's the graphical view of this so-called rollout procedure, looking at an horizon 3 into the future. So I'm here at time n. So either I add a new design and then I will replicate 3 times, or I replicate and then I have the same choice. Do I add a new point or do I replicate? So on a small example, that was this function. So it has larger noise variance in this region compared to the rest. So that's the noise variance here. And we look at minimizing this global accuracy criterion. So we start with a very simple design, 21 equispace space, 5 replicates. So if we look at what happens if we replicate first, then, so if we add a new point first, then replicate, compared to the alternatives, we see that in this case, the best thing to do was actually to replicate 3 times at the 6, 5, and the design number 6, design number 5, design number 7, and then add a new point. Also, if you look at the new points values, they change over time. It's because if you replicate at some point, then you kind of push the new designs away from these replicates. So the idea is that by looking into the future, you actually change the locations of the new points rather than taking directly a new point. Then how far away should you go into the future to make your decision? So what's costly here are these like continuous search for the next design. The rest, the replication, that's super fast to compute. So we had some strategies to handle this. So for instance, you can choose a fixed horizon, like 3 in this context, or you have some target ratio of replication, and then you look at how well you do for this. So it's like, am I adding too many new points compared to what I wanted to do, or am I replicating too much? If I replicate too much, then I decrease the horizon, so the number of steps I look into the future. Or if I don't replicate enough, then I will go further in the future. Because the further you look in the future, the least effect you will have to add a new point. Otherwise, in this context of IMSP, you can also, there is an optimal ratio of replication that you get on the points that you already visited. So you can show that what you should have done afterwards, you can actually get the best possible balance between the different designs. So how many replicates should you have done if you knew beforehand what was the noise variance? So you can compare to this and see if you are doing okay or not. So another illustration of this idea is that if you don't do any look ahead, you won't replicate much. So here replication is marked by these small bars. And the higher they are, the more replication you have at a given location. So the ratio of replication is rho. So here it's very close to 1. And in fact, you only replicate at the corner of the 0, 1 line here, because it's numerically what will happen. Then if you use a look ahead scheme, here it was the adaptive one, then you do replicate more often. And then the second part is comparing constant noise model with heteroscedastic one. And as you can see, if you have heteroscedastic noise prediction, you put more unique designs in the region where the noise is larger, which is what you want to do. And if you actually look into the future to enforce more replication, then you have more replicates in the region where the noise is larger. You can actually also do it for other acquisition functions. But for these, you would need to approximate the future evaluations. The problem here is that you don't know what will be the future value of the function, so you need to use a proxy for this. But the same principle can still work. So for instance, here it's a contour finding problem with I think it's the same function or very similar function. So when you have a larger noise, you do replicate more, and also it's on a larger area where you do replication is larger than when the noise variance is smaller. And you can have a lot of replicates dynamically. All right, and then if you do optimization, here, as you can see, you add many new points close to the optimum. And you can sometimes, depending on the runs, you can also explore various local optima. All right, do you have any question on this scheme? No? Okay. So the cool thing with this one is that it can go very far away in the future, and you have only a gentle way of pushing replication by adjusting the horizon. Now you can actually have other ways to enforce replication. So one way is through the acquisition function and having a cost. So to motivate this, so that's another one that I've started to work on, that are quantum devices. So say you have a ground truth, then you have a simulator, and you can average many times. So for instance, if you average only 10 times the outcomes of what you get, you cannot really distinguish anything. Then if you start averaging 100 times, then you can start to see some feature, but you won't be able to locate the optimum very precisely. And then if you do 1 million reps, you are much better. But then you have wasted a lot of values on non-interesting regions. So for this one, the acquisition function will be the expected improvement. So that's this expression. So as you know, you maximize it to get the next design. But the issue with this criterion is that it's really made for the deterministic setup. One typical issue is that expected improvement is myopic, meaning that it does not take into account what I will do next, and also the predictive variance. The expected improvement is the same if I consider that I had 10 replicates or 20 or just one. So a more interesting variant of based on improvement is the so-called conditional improvement, which uses the updated variance. So the point is that it's the improvement at a reference location X if you add a new location, the point at a new location xn plus 1. So you look at the effect of a new point on the improvement at another one, and it has been typically used after integration. So you integrate the change in improvement after adding a new point. But that's, of course, not something you want to do because you have to integrate this criterion, and then it's a very difficult integral. So to illustrate this, say you have this, you are in this state, you have made some observations, you have a lot of noise, so you are not interpolating at all. And you look at the conditional improvement if you add a new point in 0. So now, if you do this, so you can compute the expected improvement that will tell you to add a point in close to minus 0.5. But you can also look at the conditional improvement if you add 1 point. So that's the blue line. So as you can see, compared to the expected improvement, you reduce it a bit. That's the effect of adding 1 new point, because it decreases the variance around 0. You can also see what would be the effect if you add 1,000 replicates, and then you get the gray line here. And if you actually don't really look at the conditional improvements, but at the reduction in conditional improvement, so that's really the expected improvement minus the conditional improvement. So that's the reduction in improvement that you enforce after adding a new design. Then that's a criterion that you can use for optimization. So there is actually a link that can be made between looking ahead and also having parallel criteria. And I will come back to this. But first, my main point here is how do you do replication in this case? Because you see that the more you add replicates, the more you reduce, but the change in between adding 1 replicate and 10, and then adding 10 and 100, the change is actually way more if you do 10, and then the 90 ones that you would add to get this much you get a monotonic decrease in interest of adding a new point. So that's something you can use. So you can just balance how much increase is worth depending on some cost function. So for instance, you can define some evaluation cost and you divide the reduction in improvement by this evaluation cost. So this is what I've done in this cartoon. So I have the reduction in improvement, and then I divide it by a function that is actually, I divided by twice, by the cost of, by the number of replicates divided by 2. So I'm assuming that I can make 2 evaluations at once, and I look at how many I should do, how many replicates should I do, and when it becomes less interesting. So if you look, actually this time the blue one is not the best. The best one is the 2 replicates, the cyan line that is going the most, that is giving me the higher value. So that's comparing the NR scenario. And then the black one is another strategy. It means that I want to stop replicating when the reduction in variance becomes too small. So say I can look in the future, when does the predictive variance decrease after adding one new point will become less than, say, 5%. So I say I don't want to waste too large of a budget on a new point if it does not reduce the variance by more than 5%. So that's what the black line is giving. So this one is actually, it's another way to balance the number of replicates with the location where you add the new point. And also it's perhaps not super easy to see, but the location of the optimum of the function is changing a bit depending on the number of replicates. So usually the new points that you would add would be different depending on the number of replicates that you make. But this is just one criterion that you can compute. If it's just one evaluation of the criterion, you don't have to make a very difficult search.
Right, I've got a question. It's probably a dumb question, but what happens when the cost of the evaluations is equivalent to evaluating anywhere? So like replication cost is identical to.
Sorry, I'm not sure.
So if you like here, you said that the cost is the number of evaluations divided by 2, but if that was 1 instead, so like the replication cost is as cheap to measure a replica as to measure anywhere.
So here it was mostly for illustration. So in this specific case, then if you only divide it by 1, this one not replicating is the best. So it's really how much worse how do you define the cost function for replication? And if you can say you don't have access to parallel evaluation, then you would put less weight on replication.
Okay.
But you really
yeah, I think I'm just struggling. Would it always be? Would this always give you that the best thing to do is to evaluate somewhere else? Or
no. It's really a case-dependent thing. During the optimization, it will do sometimes not replicate, and then once the noise variance becomes too large, then it will be the important thing to do.
Cool, thanks.
Yeah. So one variation out of this is actually to look at a hybrid, in fact, in between just the reduction and improvement and the integrated version over the entire domain. So say you have a trust region, in a trust region context, you have 2 points of interest. That would be the trust region center, the next point that you would evaluate, and that can also be what's your estimation of the best points at a given time. The cool thing is that if you look at this parallel reduction in improvement criterion, you can express it simply as a function of the parallel expected improvement. The only change is that instead of using the predictive mean at times n, you use the predictive variance at times n plus p. So it does not depend on the future evaluations, and you can still have a parallel criterion. And if you look at this criterion, then in some cases, you will see that it will want to replicate, and in some other cases, it will look at 2 different points. So it's another way to push replication, is that say I want to reduce also the improvement at several points. So that's really what the idea is. I want to reduce the improvement at this xk point, x star, and at the future points that I would add. Then I enforce somehow that I want to add points close to these ones, and then that will push towards replication. So that's so as I said, there is a clear link between looking ahead. So that's the most expensive thing that you can do is like to look far away in the future. In practice, you can look at the parallel version of the same criterion, and that's an approximation to the step the looking ahead version. So that's actually using this fact that if you take a parallel criterion, then you are approximately doing some look ahead. And if you are using a criterion that's interesting to you, like this one that is using the trust region center and the estimated optimum, then you can enforce replication. So we tried it, and just here a quick example on the quantum device I showed. So 4 variables. And the comparison was quite simple. It's either you do BO with 100 iterations with 100 replicates, or you allow for the use of a death criterion that is giving you the replication budget at the same time as you do the optimization. So as you can see here, there are much less new points, and you have a replication occurring in many parts. And in this case, here you get a better regret, and then it stops because it cannot find more an improvement.
Mickael, just a quick time check. We've got 5 minutes left.
Okay. Maybe do you have either I go very quickly on the third option, or we discuss this example more. It's up to you.
Maybe the example.
Sorry? I go for the last option?
Go very quickly then.
Yeah. Okay, so I will skip over the multi-objective optimization, that you want to be better in both objectives at once, not always possible. So you look at Pareto optimal points. You don't really, it's noisy, so we look at expectations over the objectives, and we use the hypervolume criterion to make decisions. So in this context, if you were to do a batch optimization, so the QEHEI, that would be a very difficult problem, especially if you have many points that you want to evaluate. The difficulty comes from this optimization problem, that if you want Q new points in dimension D, either you optimize a Q times D acquisition function, or you do it sequentially, which means doing it Q times this problem. And knowing that even if you have a simple EI function, 50 points, it's already a difficult optimization. So you can imagine if you have 100 points to add in parallel, then optimizing this would be quite difficult. So that's a motivation not to use batch criteria when you have a large batch size. And the idea, so you had this plot to show that if you go from Q equal 5 to Q equal 50, you really degrade what's going on for the optimization of the original batch criteria. So the idea is that you look at the predictive mean, predictive variance Pareto front. If you are using QEI with 5 new points, then the points that would be proposed would be close to the Pareto front or on it. If you do it in dimension 50, you get many points that are actually very far from the Pareto front, and you can show that they bring no improvement. So a way that we use to select many new points, but not using these expensive criteria, was to use some idea of an allocation, a portfolio allocation. So you define a return by the value that you improve over by the mean value, and the risk given by the predictive variance. Then there is a simple portfolio criterion that is called the Sharpe ratio, which is a balance between the risk, the return that you get divided by the normalized risk. And if you use this on the on your multi-objective problem, then this will give you actually weights. And from these weights, you get the number of replicates that you should do at possible candidate batches. So that's the key point with this variant is that the objective that you actually optimize would be super fast. That's the mean and the variance of a GP. You can use gradient-based optimization. And since the output of the method is a set of weights, then you have replication. You can change the size of the batch adaptively. So we tried this. So the key points on the experiments are that it's not such a bad idea. Of course, it's not as good for small Q values because you won't do better than the best infill criterion. But once you increase Q a lot, and when you look at time, then it's clearly a good thing to try. And to close back to the beginning, on the CT-COVID problem. So we tried it with Q up to 4,000 evaluations at every 4,000 evaluations per iteration. So we had to make some changes to make it work. But the idea was that given a set of 5,000 observations going up to more than 200,000, we got better results with the strategy than what you would have got with random search. And the key feature of this problem that was a bit surprising, or at least not super surprising, but that was annoying, is that if you look at the estimates of the Pareto fronts at the different rounds, in fact, you can see that they were super optimistic at first. And once you start refining, it actually degrades. And once it stops degrading and improving again, you know that you have started to do a good job at estimating the Pareto front. But at first, if you don't replicate and you don't have enough data, then your Pareto front estimation is quite bad. All right, so in conclusion, so when you are looking at noisy simulators, there are many challenges, but there are also many things that you can do. And even though one individual evaluation may not bring you that much information, it also means that you should consider replicating in your acquisition function strategy. So there are many ways to enforce or not replication. And I've tried to give you some ideas in between looking ahead using batch criteria or just using some mean and variance arguments. And there are many ways to try to tackle even more difficult problems. Thank you for your attention, and thanks also for the questions.
Thank you. I think we're slightly over time, so if people need to join other meetings, now is the time to do so. For people that can afford more time, you can stay and discuss a bit more.
Okay.
I've got some dumb questions. But I'm happy to go second if people have more intelligent questions than I do. Cool.
Yeah, go on.
Can you go back to slide like 14 or so? I can't remember exactly the right slide, but right when you're talking about the GP formulation, basically.
Okay.
Maybe it's so maybe it's a couple of slides back. Basically, so you're fitting a GP for your latent mean function, basically, and then you've got this separate GP to model the noise.
Yeah.
So you can do the predictive density. So and the second GP is being fit on empirical noise estimates. So I guess the formulation that you're using is better than, so like there's something similar that you could do which seems a bit worse, but I'm just trying to understand the ways in which it's worse, which is you could fit your first GP on like empirical mean estimates, right? If you've got these replicates, you could estimate the mean and the noise, and then you could fit 2 GPs for each one. And I think what you're doing is a bit cleverer than that, but I may be missing some of the intuition for why it's better.
So like the idea of using 2 GPs, one on the empirical mean, one on the empirical variance, and combining them together in the sense that the one on the mean, you use the predictive variance. That's completely fine. It's just that you need to have enough replication for it to make sense.
Yeah, exactly.
So then if you cannot really make it, then you need to have a latent GP. And for the latent variables, what can help is that if you have replicates, then it helps your approximation scheme, because it can use the empirical variance.
Yeah, but if you go back one slide.
Yeah.
This isn't equivalent, like you're sorry, I mean maybe I'm misunderstanding, but the R function is fit on the empirical noise estimate in this instance, but the mean you're just using Are you just using all the data, or are you actually fitting on the empirical mean? I think you're not, though.
Mean. For the mean, it's directly the empirical mean.
Oh, is it? Okay, fine.
The
Makes
noise
sense.
variance is actually just in the covariance matrix.
Yeah, okay. Cool, thanks. This makes sense. Yeah. I think, yeah, if you don't, I've got one other question, I think. So if in a setting where it's not important to estimate the noise, like there is noise, but we don't care about the noise. We only care about the mean. Would you say replication is still important?
For speed, yes. Like if you get still a huge speed bumps with this, and also it's really, so if your noise variance is quite small and it's more or less constant, clearly, yeah, replication may not be your main concern. Once you start to have very low signal to noise ratio, like in the CT COVID application, not handling this, not really taking into account the noise is actually hurting. So that's like what I was showing here. So at first, what we did try was to do some expected hypervolume improvement and then doing some fixed amount of replication. But it was not working super well because the estimate of the Pareto front was wrong. So in this case, if you don't filter out the noise variance and making it also heteroscedastic, because and in this case, it was quite heteroscedastic, then you lose a lot. So I would say, yeah, it really depends on if you have a complex noise and a low signal to noise ratio, then it's more important to replicate.
Well, thank you. Yeah, very helpful.
So Mickael, I found a bit counterintuitive your result that replication is optimal, but maybe that's because you care about the mean only. But it seems that you always get more information if you don't replicate, but you go next to it.
So I can go back to the result. So it was a result for the IMSP. So it's really looking at the predictive variance. But still, the trick in the example I show is that the noise variance would change, would augment a lot next to this point. So there is this ratio in between what will be the accuracy of the observation that you make. And if you have the noise variance is increasing too much and too quickly around this point, then it's better to replicate. That's really what's going on in this case. So you can play with the shape of the variance function. And if it's like the green version, it's actually the noise variance is decreasing, so there is no incentive to replicate. And of course, you would add a new point where the noise variance is lower. So the point that you can borrow information from at a bit at some distance, and it depends on the noise variance.
I see. Okay.
And the second part that was on the expected improvement. So I went too quickly on this, but still, like if you start looking at several targets at once, then it's also enforcing some replication. And that's what you can see here. Here, numerically, this criterion. So it's looking at the location of the next 2 points. And it's depending on the budget that you use. If you do one replicate here and one here, then they will be the same. So replicating is optimal. And it's when you start adding more points, then having a new point will become interesting. So that's the feature that you can see in this example. You have 2 local minima. So at first, it's better to do 2 replicates at one location that's close by here, because you want to improve on the minimum on the center. But if you have more budget, at some point, it becomes interesting to go also visit the second local optima.
That makes sense. And I guess that for the first case, the IMSP,
Yeah.
the noise is heterogeneous. If
Yeah.
it has a constant noise, then the replication is.
It's never optimal, yeah.
Thanks.
So I've been working a bit more now with the trust regions. So you can argue that at some point, so it's at first it's good to have heterogeneous variance modeling, because that it's maybe a feature of the problem. But once you reduce enough the size of the trust region, then you can take a constant noise. That's sufficient.
Are you familiar with the modification term? In optimization literature, modification means that you kind of injecting noise in the data, and there is this property that your loss function becomes more stable, or like it's smoother compared to what you would have if you got just data. So basically, this modification, if you know these diffusion models, like basically this they diffusing the input into the noise, and what they actually do, they do the modify the data like step by step. So it seems like this technique of actually replicating data points is quite similar in some sense, because you kind of just have a noise parameter for this data point, and you add some extra target value there. I wonder if actually there is any connection to this basically or not. So
it's a very good question. I don't know, but I will take a note to check this. Yeah. Okay. And to me, yes, something I did not say. Also, it's from an optimization context, like just from the user point of view, having in between having like you at some point you need to return a solution. And I think if you give a solution like on a noisy problem, when you actually can show the replicates, it's better than saying, oh, I give you this solution, that was the evaluation I did. But if you repeat it, you may get something way worse. Well, if you can say, oh, we have replicated, I don't know, 10 times, and that seems to be robust, then it's more convincing in a sense. Like it's really, again, back to this example, multi-objective example. So at first, the estimate of the Pareto front was too optimistic, so clearly driven by noise. But once you have replicated enough, so in fact, what occurred is that you have this estimate of the Pareto front, say the red one, that is clearly over-optimistic. Then you start replicating on this estimate of the Pareto front. And what happens is that these points that were good with 1 or 2 replicates, once you have made another 10, then they would appear to be way further. So it's really like you have to eliminate the noise before you have a clear target. That you cannot really do if you just take individual evaluations. Take you a lot of evaluations to get rid of a wrong estimation that you would have on this given this single point.
I think we have no more questions from the room. I don't know if there are any from online. Spaciously quiet.
Okay, it doesn't seem so. So okay, let's stop here and thank Mickael again.
Thank you for the invitation. And
Thank you for a great talk.